Hello, my name is Mark Edelman, and I will be talking about finding periodic points in fractional systems. Now, why is it important? First of all, in regular dynamics, not only in fractional dynamics, the study of dynamics begins with defining those periodic and fixed point and bifurcation diagrams. Now, if we are studying chaos, then it is known that in this case, periodic points are dense and they comprise skeleton of classical and quantum chaos. Now, what is also known that fractional systems, they don't have periodic solutions except for the fixed points. How to find periodic things which are asymptotically periodic solutions of fractional maps. This presentation will follow the paper published in archive, not in journal yet. So the question is how to find periodic things. This is the question. Now, talking about maps, there are two widely accepted ways to derive maps. In one case, when we derive them as in regular systems using differential equations of Kick systems, we derive fractional maps. And this is fractional maps, which is a convolution with power law function. And everything here is quite clear. Now, the other way to derive maps is to solve fractional difference equations. And in this case, the map will look like this, which is almost the same as a previous one. And also the previous one has a time step h, which is actually time between two consecutive kicks. Here, h is a step in fractional difference equation. So solution of h difference equations can be written in the following form, which we can consider as fractional maps. Now, again, in the regular maps, here we have power alpha minus 1, okay? But in fractional, we have this those parentheses. And the meaning of those parentheses is here it's fallen factorial, and here it's h fallen factorial, but they are asymptotically power law functions. So asymptotically, those maps are the same, but those moments near the present moment play quite important role and define difference between those two maps. Now, both maps can be written as the following convolution. Simply, G tilde is defined through GH and gamma function, and U is a little bit different in two maps, fractional and fractional difference. But if we find periodic points here, then using those substitutions, we may find periodic points in fractional and fractional difference maps. Let me see. Okay, yep. So here we are. Now, the previous formula, this big formula, which defines fractional maps can be rewritten for L cycles, defining m's element in a cycle after n cycles. And then this total can be rewritten as L totals, each with regards to certain position of element in a cycle. So we have this series initial, it's total of elements, first, second, so L's, then L plus first plus second, and so on, and so on. And here the total is rewritten as L totals along those columns. Okay. And then let's consider differences. Why differences? Because those elements itself, they converge to zero, but corresponding series, they diverge because the order is alpha minus one. But here, the order of this difference will be this n, let's say, to the power alpha minus 2, and for alpha between 0 and 1, and this is the only case in which the maps are with fading memory, not with enhancing memory, where the role of previous states is fading with the time increasing from the present moment. And in real biological and socioeconomic systems, it's known that alpha mostly between, almost always between 0 and 1. So here we'll have a convergence series. Okay. And then let's assume that L cycles do exist. In this case, we may consider limit as n goes to infinity, and the previous equation can be rewritten in the following form. And if I don't have time to go into details, what actually is done in this paper is based on almost everything, or some modifications based on the following property. So this theorem, limit as n goes to infinity of the total a n minus k b k equals 1 to n is equal to a s, where a is the limit of a n minus k, or let's say, no, not a k, as k goes to infinity. So this limit must exist. And S is the total of bk. So series B should be conversion. If we look again here, we assumed that X convergent, so G will also converge to certain value. It's our A. And this series is convergent. So this theorem, I don't know if it exists, but in that archive paper, it is proven for this case, in this case. And the proof is based on division of this total into two totals up to n1 and for n minus n1, which goes to infinity. So we divide the series into 2. And then using epsilon delta, in this case, epsilon n formalism, we can show that this will converge to corresponding totals, will converge to the following totals. Where S, so G are limiting values of function, and corresponding totals here. We have L totals, but they are not all sorry, independent. Total of all S from 1 to L is equal to 0. So finally, we are getting L minus 1 equations for differences of limiting values in L cycles. So those are equations. But here we have L unknown and L minus 1 equations. To close the system, we consider the total of all limiting values of X. And it can be rewritten and it can be shown again using considering limits as n goes to infinity, and using splitting total into 2 totals, as it is done here, and again using epsilon n formalism, we can show that the only case in which the solution of that equation is possible is when this total is equal to 0. Now, let's summarize what is done in this presentation, and mostly in that archive paper. So first of all, we derived the equations which allow calculation of the asymptotically periodic points for fractional and fractional difference maps. This sets the framework to analyze bifurcations and chaos in discrete fractional systems. So first, calculate the values of coefficients Si, and it was published not values of S but results for different maps of fractional and fractional difference, only for period 2 points. I also have results for period 3, and we're doing more here. Then specify the values of H and function G for your map. Use some methods, for example, L-dimensional Newton method to solve equations for L-cyclic points or periodic points. Start with a known value for alpha equals to 1 and proceed with small steps in alpha and k to find critical values where bifurcations occur. And then to analyze chaos, place those periodic points on phase portraits or return maps and look for the results, analyze the picture. Thank you very much. And this is the end of my talk. I have to stop recording.